All right, guys, today we're going to look at the problems on electrical circuits, the word problems. So first, let's go over the formulas you're going to be using. The first formula is the standard formula for electrical circuits, and that's Ohm's law, which relates voltage or potential difference, current, which is I, and resistance, which is R. So you have the current times the resistance equals the voltage or potential difference. So that's Ohm's law. Next, we have the resistivity formula. The resistivity formula is the one that allows you to find resistance and resistivity. So you have R, which is resistance, equals the Greek letter rho, which looks like a lowercase p, times length over cross-sectional area. So resistance R equals resistivity, which is the Greek letter rho, lowercase p looking thing, times length over area. Area has to be in meters. Length has to be in meters. So area will be a meter squared, length in meters. And then this is an ohm meter, and this is a constant for each material. So each material has its own resistivity. So I will either give them to you, or you'll have to Google a table if that's the case, but I'll try and give them to you, because usually we would use the textbook. Okay, next we have the power formulas. And there are three power formulas that you can use. You can use the power is voltage times current. So that's one formula. You can do power is current squared times resistance. Or you can do power is voltage squared over resistance. So any of those three formulas will give you the power. And it just depends on what you're given in the problem, which one you use. Finally, you're going to use Joule's law to find energy. And that formula is basically that energy is power times time. So those are our formulas. There are 1, 2, 3, 4, 5, 6 of them that you need to know how to use in this unit. This one, these three for power, and then this one for energy. Okay? So now that you have the formulas, we're going to work through the examples so that you know how to use them, how we're going to apply those formulas. So the first one, if you get your example sheet out, on your examples, you have a resistor of 200 ohms. So R equals 200 ohms is connected across a battery with a potential difference of 12 volts. Potential difference and voltage are the same person with a different name. So 12 volts. What is the current in the circuit? So we're looking for I. So this is obviously an Ohm's law problem, which I told you here. Usually you won't get that little label. So V equals IR. We know the voltage is 12. We're looking for the current, so I is our variable. And we know the resistance is 200. So you're going to take 12 and divide it by 200 to get your answer. And your current works out to be 12 divided by 200. .06 amps. Okay, 0.06 amps. So that's our answer to problem number 1. I is 0.06 amps. And remember, we were given resistance and we were given voltage. All right, the second problem is a resistivity problem. So we have a 20-meter long piece of wire. So the length is 20 meters. We have that the wire is 12 gauge. That doesn't really mean anything to you or to me. It's just basically how wide the wire is. The bigger the number gets, the smaller the wire gets. It's kind of a reverse relationship when they measure gauge. But we don't use gauge. All we really need is the diameter. So the diameter of the wire is 0.002053 meters. Diameter is not what we need. What we need is radius, because we want to find the cross-sectional area of the wire, which is a circle. So we need the radius. The radius is going to be half of the diameter. So half of 0.002053 gives me 0.00100265 meters. Okay? Now, the area we can find by doing pi r squared, because it's a circle. And pi r squared is the area of times 0.00100265 squared is going to give me my cross-sectional area. And I get 3.31 times 10 to the negative 6 square meters. So that's my cross-sectional area. Rho was given to you. The resistivity was given to you right here. Okay, so that's your resistivity. And so now you can plug into the formula. You're looking for resistance, rho times length over cross-sectional area. So we have 1.72 times 10 to the negative 8. You're going to multiply that times the length, which is 20, and then divide by 3.31 times 10 to the negative 6. And let's see what we get. So we have 1.72 to the negative 8 times 20, and then divided by 3.31 to the negative 6. And that gives me 0.104. So 0.104 ohms is my resistance. That's my answer. Okay? Moving on to the third example. The third example is a power problem. So you're being given a resistor of 50 ohms. So we have resistance given, 50 ohms. Has a potential difference of 2 volts across it. Remember, potential difference and voltage are two things that are identical. They just have the same name. They have different names, but they're the same thing. And we want power. So go back to your power formulas. We have 3 of them. We don't know current, so that eliminates this one, and that eliminates this one, but we can find power using this third equation. So I'm going to say that power is V squared over resistance, voltage squared over resistance. So 2 squared divided by 50, in other words, 4 divided by 50 gives me 0.08 watts. And watts, remember, is the standard SI unit for power. So that's our third example. Okay? Our fourth example, another power example, because I'm trying to give you little different look at each of the power formulas. You have a 25 ohm resistor. So again, power is given to us. Resistance is given to us, 25 ohms. And you have a current of 4 amps going through it. So I is given to us, 4 amps. And you want power. So looking at the variables that we have I and R. The middle equation will work for us. The P equals I squared over R will work for us because we don't know voltage. So using that equation, I squared times R, I meant times R, not over R. We have 4 squared times 25. So 16 times 25 gives you 400 watts. Now, what if you were asked to convert that to kilowatts? If you wanted kilowatts, you would divide by 1,000, and that would give you kilowatts. And so that would be 0.4 kilowatts. It just depends on what the problem is asking for. Okay? All right, next example, number 5. This is an example of Joule's law because you're being asked to find energy. So it says an old black and white TV set operated on 90 watts of power. So power is given to you. The power is 90 watts. If this TV set operated for 2 hours per day, so we're being given a time period here, for a 5-day period. So in other words, my total time is going to be 5 days times 2 hours per day, so 10 hours. Now we're going to have to convert that to seconds because we can use hours if we're finding kilowatt hours, but if we need to find joules, then we have to convert it to seconds. So there are 3,600 seconds in 1 hour. So 36,000 seconds were used. I want energy in both units, in joules and in kilowatt hours. Joule's law tells you that energy is power times time. So power was given to us as 90 watts. So if I take 90 and I multiply it times the time in seconds, 36,000, that will give me the energy in joules, which is the standard unit. And I get 3,240,000 joules. So that's the energy in joules. That answers part of the problem. We want the energy to also be found in kilowatt hours. So where the joule is a product of watts and seconds, the kilowatt hour is a product of kilowatts and hours. So 90 watts is the same thing as 0.09 kilowatts. You divide by 1,000. So we have 0.09 kilowatts times 10 hours gives you 0.9 kilowatt hours. And you can kind of see why the electric company prefers to use kilowatt hours over joules. Because you use 3,240,000 joules just to power a simple black and white TV set for 10 hours. And in a month, how much energy do you use? You use a lot. So kilowatt hour is a much more convenient unit because you end up with smaller numbers. All right, finally, the last example is on cost. because we're dealing with electricity, and this is something that costs us money. It's one of your most, other than your mortgage, one of your higher bills in your house is the electric bill. We want to figure out how to find cost. So we have an Olympic. You're watching the Olympics, and your TV set is a color TV, 500 watts. So that is our power. Okay. So the power is 500 watts. In kilowatts, I would divide by 1,000. And we're going to have to use kilowatts because that's what the electric company uses. So divide by 1,000, you get 0.5 kilowatts. Okay, you're running the TV for 17 days, watching 3 hours per day. So our time unit is going to be in hours. We're going to have 17 days times 3 hours per day. 17 times 3 is 51 hours. And I'm just going to keep it in hours because I want kilowatt hours anyway, since that's what the electric company uses. So energy is power times time. So 0.5 times 51 tells me that I used 25.5 kilowatt hours of energy. Okay, that's the amount I used. Now this is where the cost comes in. If I want to know how much you would pay for the use of that in your electric bill, you would have to know how much your electric company charges. So let's say that the electric company charges 12 cents per kilowatt hour. Okay, and that's about a pretty good idea of what they do charge. So you have 25.5 kilowatt hours times 12 cents per kilowatt hour. So you can see that the kilowatt hour cancels and you're left with a money unit. So you can figure out costs. So 12 times 25, or 0.12 I should say, times 25.5 means that it's going to cost $3.06 to watch the Olympics. And that's how you do cost. So it's really just a matter of being in the right unit. You have to be in kilowatts, which means you're going to take your watts and divide by 1,000. And you have to be in hours as far as your time, so that when you multiply power times time, you end up in kilowatt hours, which is the unit you want. And then multiply it by the cost. And that's it. So those are your problems. You have your homework to work on, to practice. So do those problems. They're due by midnight tomorrow. All right, thanks. See you later.